Morning and welcome to Android for Java developers. This talk is a wrap around a series of very long articles that I hope everyone will read eventually, called Developing for Android. So if you go to medium.com and search for that phrase, or if you just go to the internet and search for that phrase, you'll wind up on the series of 10 articles. These came out of an incredibly long doc that we wrote internally at Google when we were faced with a bunch of app developers we would meet with on a regular basis, and someone said, so every time we talk to the framework team and we say, we're doing this thing, and then the framework team says, no, don't do it that way. Do it this other way instead. And then they'd go away and they'd do that, and they'd come back with another question, and we would say, no, that you shouldn't do that. What you should actually do is this other thing instead. And they said, okay, so where do we go for the information that sort of collects all these tips and tricks and techniques so that we can stop getting slapped by the platform team for the way that we're approaching this stuff? So that was the genesis of the article. We decided to actually take a step back and say, okay, what are all the things that we think are obvious, but typical Java developers do not? And the problem is that a lot of developers, most developers writing Java code at Google come from the server world, or even the desktop world, sort of traditional Java platform. And then they say, okay, well, this is the same language, so I'll carry over all my patterns and practices from that other world into this little tiny mobile device with a constrained CPU, GPU, memory, limited bandwidth, like very, very different programming environment. Really, the only thing that is the same is the programming language itself. So the way that you use that programming language is very important in terms of the performance and the experience that you're going to get in the end result of your application. So we wrote this huge article, we put it out internally, and then for the short attention span public, we broke it into 10 still very long articles on Medium. So please check those out. In the meantime, I wanted to walk through some of those today. If I tried to go through everything, this would be about a 3-hour talk. We tried this once. We gave a talk at a user group in the Bay Area, and we put together this a version of this talk, and we made it about a quarter of the way through in 1 hour and 20 minutes. So yeah, actually 3 hours is an underestimate as well. Because each of the topics, like, they're little tiny bullets, but they're kind of deep crevices that you can go on at length about. So I thought instead today, instead of trying and failing to cover everything that those articles cover, I wanted to talk about the memory situation, because a lot of the performance concerns and a lot of the problems that people hit are in the specific area of memory. That's really where a lot of the performance problems and bottlenecks come from, partly because the runtime and the garbage collector are vastly different than what you might expect. So I wanted to start out first by talking a little bit about how garbage collection and allocation actually works on Android. And then we'll talk about some of the tips and tricks about memory in particular. And then maybe we'll talk about some other stuff as well. We'll see how far we get. So first of all, I want to mention that one of the important things that we see in terms of device usefulness or application niceness is what we call the tragedy of the commons. And this is an effect where every application will work in its best interest. It will be necessarily greedy, because obviously if someone has installed my video playing application, it's really important to them for the user to actually watch the videos in my application. So I'm going to sync all the time, and I'm going to make sure they get the most up-to-date data, and I'm going to allocate tons and tons of memory so that I have all the stuff cached and it's just ready to go all the time. The fact is, the user has many, many applications installed. Yours is one of them. And if it's too greedy, yours will not be one of them for long, right? If every application acts in this way, and they do tend to by default, then it makes the overall device experience suck, right? If every application is allocating too much memory, if it takes up too much heap, if every process is huge, then the task manager will continually be killing all of the background applications in order to make the foreground application have enough memory to run itself. And then when your rather greedy and bloated application goes into the background and the task manager says, well, I'm running out of memory, I better go look for some large memory users, it's going to find yours and it's going to kill it. And the next time the user goes back to it, it's going to have to relaunch and do a cold start because it was killed, right? Wouldn't it be nicer if all the applications were more slim and trim so that whenever the user switches between them, they can do so easily because they just have to page them in instead of actually reloading and relaunching everything. from storage. So there's sort of two effects that we see. There's the tragedy of the commons, where everything is greedy, and then there's the every device is a village. So not only are all the applications greedy and they are suffering for it, but then the overall device is suffering for it. You know, now the user experience from all these greedy applications on the device is that they're constantly relaunching all of the activities there, or some service running in the background is syncing, causing performance problems in the CPU to be doing things for absolutely no reason whatsoever. I'm not using that service right now. I haven't used that e-reader for a month. Why is it actually syncing in the background when I'm trying to use another application in the foreground? So these two effects are very interrelated and contribute to the overall user experience of Android. So the goal of this article and of these tips and practices in general is to help application developers write better applications so that we can make the overall platform better. So let's go talk about memory. Three dynamics to be aware of is that memory is limited, and this is far more limited than you might realize. Living here with our less constrained financial resources and more available technology, we tend to think of like 1 gig as being the low end. You know, there are devices with 2 gig or more readily available, so surely this is what people have in the real world. In the real world, low-end devices are still being used because they were sold several years ago, and people don't just ditch devices for new ones unless they're like the people in this room. Maybe they don't actually, you know, have enough money to go buy a new phone whenever they're excited by it. So they may keep that device around a lot longer than you, the developer, want them to. So they're running with a low memory device because they bought it a while ago. But the more insidious dynamic is that there are still devices being sold with low memory in markets where money or technology is not as readily available. They may be selling these phones to people that, you know, are really excited about getting this new device that only has 512 on it. Right? Not much memory. It's a new phone. What are they doing coming out with that amount of memory? Well, this is the configuration that made sense in that market. And there are a lot of these phones still being sold out there. So even though you are running a device that you don't consider high-end and you think the memory problems have gone away, they actually haven't. And they're going to be here for a while because of those two dynamics. So it's very important for you, the developer, to realize there are these low memory situations and to make sure that your application behaves reasonably well when one of those situations occurs for the user. The other issue, as I alluded to before, is that that memory is shared. Everybody is swimming in the same pool. I don't really like that metaphor. So everybody has to behave if you want the overall experience to be good. If your application is greedy and every other application is greedy, the entire experience of the device will be horrible, right? Because everybody is constantly going to be shoving everybody out of, you know, CPU cycles as well as memory. And then finally, memory equals performance. And this is the one that I want to spend a little bit of quality time on today and explain what we mean by that. So first of all, let's talk about memory. Let's talk about the garbage collector and how it actually works and why we see some of the performance issues that we do. So there are three things that cause memory to be expensive in terms of performance on Android. One is the allocation, the process of actually creating memory for the new objects that are being allocated. The next is concurrent collection, or just collection in general, when we actually need to clear things out so that we can make room for other allocations that need to happen. And then the third tends to be the most painful one, which is collection for allocation. If anybody has taken a look at log and looked at the GC information in there, this is commonly referred to as GC for alloc. It's a situation where you go to allocate something, there is not a free space in the heap, and then the garbage collector needs to run synchronously right then to free up enough memory to store your object there. So let's go into some of the details there. We can see the four phases of normal allocations and collections here. You have this new object on the left next to the squiggles, and we need to find space for that. Oh, fortunately, there's a space right there. We'll pop it in at the top. This is an unusual situation where it was really easy to do that. So once that's there, then we enumerate all the objects to figure out what's still referred to in the heap. You can see the red one doesn't have a reference there. We mark all of those to make sure that we know what things are still referred to and what things can actually be collected, and then we collect. And you see the red object goes away there because there was no reference to it. So we can collect that now and free up space in the heap. Okay, so on Dalvik, there's actually two pause times that occur in the normal process of simply allocating and collecting. There's a pause time to enumerate, so we basically stop the world, the GC thread runs alone in the process, everything else is paused while it figures out what the things are in the heap during the enumeration phase. And then there's the mark phase, where at the end of that, so it'll mark all the things to figure out what doesn't have a reference there. And then it needs to run one smaller mark phase at the end of that in case there were allocations while that concurrent marking was going on. And there's another pause there. So there's a large pause potentially in the enumeration phase, and then there's a smaller pause at the end of the mark phase. And then it can collect everything, and it does that concurrently. In art, it's a little bit different. We eliminated the first pause, so there's no synchronous pause during the enumeration phase. It can do that concurrently. There is still a small pause at the end of the mark phase. It's a little bit smaller because there's been a lot of optimization work going into the collector in art. So it's better in art, but we still have a pause there. And I should point out, too, that like even when there's not a pause here, there's still stuff happening, right? So all of this is causing CPU to do things in the background, whether it's, I just turned on the audio on my screen, so look out. Even if it can happen concurrently, it still means it's happening, right? You're still taking up cycles to do these things. And in general, it's good to not spend the cycles if you don't have to. Okay, so now let's talk about the one that's more problematic. This is the GC for alloc situation, where a new object comes in, and we pop that onto the heap, and then another one comes in, and we walk down the heap, and we look for space in there, and there is no space, right? And then we have to actually run a GC synchronously. We stop the world, so we got a huge pause in the middle while we actually go and free up the stuff that we need to in order to fit this into the heap. And then we can put it in there and go on about our business. And the GC for alloc tends to be painful both in terms of time. On Dalvik, this can take 10 to 20 milliseconds, which is easily more than a frame. So you're going to potentially skip an animation frame in the middle and cause a hiccup. And then there, totally lost my train of thought. Yeah, I just gone. It turns out you should sleep at night. It also means that none of your other stuff is running, right? So it's just going to pause in the middle, it's going to do all this work, and nothing else can happen at the same time. So in general, that's a good thing to try to avoid. Art makes this a little bit better, no, a lot better, because it has a separate heap for large objects. One of the causes of having to do too many collections was that all of the objects were stored together. So you'd have these little tiny temporary objects, new of object or float or integer or whatever, and then you'd have this bitmap taking up a massive amount of space in the middle, and it would cause the heap to get really large, the amount of space that would have to be walked to be really big, and the fragmentation issues to be much greater in the heap. And now art takes all the large objects, all the bitmaps, and they live in a separate piece of memory over there. So all the big ones go out there, all the little more temporary objects go in the main heap. And it means that there are far less pauses. It means that also that the pauses are much smaller. So whereas the previous Dalvik pauses may have been on the order of 10 to 20 milliseconds, now we see pauses of like 3 to 5 milliseconds, which is much better. It's way under the frame boundary limit, which is great, but it's still significant enough that it can push you over the frame boundary limit anyway. So it's still a good thing to avoid. Meanwhile, while all this churning is going on of actually allocating objects and needing to collect them to free up the space for them, you're also growing your heap. So the more allocations you're asking for, the more you're causing the heap to grow over time. So if you just allocate more and more objects, eventually the heap is going to say, well, I'm out of room, but you're not up to your process limit yet, so I'll grow the heap there. So it'll go through A, the work to do that, and B, it'll take up more memory on the device to allocate that larger heap. And larger heap means now your task, your process is taking up more memory. There's less available for the rest of the system. You're also causing your app to be killed because you're going to be taking up more space. When the task manager is looking for background apps to kill, it's going to look for large ones because that's a lot of memory that it could take back. There's an important point to note about this is that under Dalvik there was no compaction, right? Which means that when this causes big problems with fragmentation of the heap where you would allocate these temporary things over time, and then you would remove the things that weren't there anymore, but the things that were permanent or long-lived would still be in the heap somewhere, and we could never actually get back that memory. There is a certain amount of trimming that happens under Dalvik where if we get rid of enough of the objects that occupy an entire page, eventually we can hand that page back to memory. But in general, you're stuck in this situation where you basically grow without bound. The heap gets larger, and we can never really get back all of that space, even if you only grew it to a large size very temporarily. Under Art, this improves because we do actually compact the heap eventually. When your app goes into the background, when it senses that it's an idle time, that it can do this operation, then it'll take a look at the heap and realize, well, there's a lot of objects that went away in the meantime, and we can compact the heap. So it gets better under Art, but it's still a problem, right? Especially if you're just the foreground application. We're not going to compact the heap at that time. All right, so there's a few points that come out of this. So when you have fewer allocations, you get a smaller heap. You also get faster allocation times because there's simply less work to do to figure out where the free space is. You get faster collection times because, again, smaller heap, less things to keep track of. You get fewer pauses because there's less to do over time. And there's less CPU usage because you're not causing the CPU to actually continually do this, mark and sweep and collect in the background. And then overall, you get less jank, especially for the GC for alloc. If you're constantly allocating things and then you run into a situation where there's not enough free space for a new object, then you're going to cause a GC for alloc, which in general will cause jank. It'll cause you to miss a frame, particularly on Dalvik, but also on Art, because you're basically causing a whole lot of work to happen at a super inconvenient time. And then all of this, in general, I would posit leads to happier users and world peace. I leave the last item as an exercise for the reader. Okay, so let's talk about some of the tips and tricks about using memory more effectively. We meaning me and Romain gave a talk years ago at Devox, and it's up on parlays.com that goes over a lot of the details here, like some of the sizes and quantities involved. So I would encourage you to check out the video. It has a lot of the details behind some of these items. First of all, avoid allocations when possible. One of the things that we've seen, and there's actually a lint check for this now, is don't allocate in the middle of your inner loop. In particular, if you're in like on draw and you realize, well, I need to draw to this canvas and I need a paint object, let's get a paint object. So we'll create a new paint object and we'll do this. Incredibly common. So there's like a lint check for that specific pattern, just because so many people were doing this. It seems dumb. You're like, how big can it be? There's only 5 letters in the word paint, right? It turns out it's a problem. It's a problem for 2 reasons. One is not as obvious, is that the Java level object that we're allocating, the paint object, is kind of the tip of the iceberg. We're also allocating stuff at the native level, which then needs to be finalized and collected later, which is kind of an arduous process to go through as well. I'll talk about finalizers later. So there's a lot of stuff that's happening underneath paint that you're causing to happen just by allocating a temporary paint object. The other one is the churn that I was talking about. If you are in onDraw, and if your onDraw is being called on every frame of an animation, and on every frame you're allocating a paint object, well, at some point, that means that your heap will fill up. Maybe not in that animation, but maybe in a future animation. At some point, you're going to go to allocate that paint object, and it won't find enough space. And then it's going to have to make the space. So you're in the middle of an animation, you're in your draw loop, you're on the UI thread, and GC says, you know what, I'm going to have to collect right now. Would you please hang on for a few milliseconds? And that's what causes jank for the user. So don't do that when you don't need to. One of the strategies that we use internally in the framework that I would encourage people to look into in specific inner loop situations like this is caching objects. So one of the tricks, if you ever look at the source code of the framework, like Vue.java or any of the core classes there, we will keep around either instance classes or in some limited cases static objects that only get allocated lazily. So when we see the first time that, okay, we're going to need a paint object or a rect object or a point object for this particular call, if it's null, we'll go ahead and allocate it then, and then thereafter we'll just use that shared object. In a lot of cases, so in the onDraw situation, chances are you don't need that paint object for anything else in that class. So you could have an instance variable or a static, if you want to manage it that way, that only gets used when you're actually in that onDraw method. So it seems a little silly, you might as well have a local field, but because of the memory concerns, you really want a cached object instead. So allocate it lazily and then use it whenever you need to in that specific method. You have to be careful with this. Obviously, if you're actually accessing that shared variable, either instance or static, from multiple places, that can get a little tricky. So it's not a blanket pattern. Just like all of these tips, these are not like hard and fast rules. But in general, it's an approach that can avoid the kind of expensive, insidiously expensive allocations that we see in inner loops. Pools. So object pools are something that traditional Java, certainly server developers, kind of walked away from years ago. You know, let the memory manager manage your objects for you. You don't need to. But because of the allocation concerns that we have on Android, sometimes it's a good idea to actually do this. If these are expensive objects to allocate, maybe it's better to actually have a small pool of these things and keep them around instead of having to reallocate one every time you need it. This also can be tricky if they're being accessed from different places in the code. Then there's a bit of management overhead to go with this. This is not as easy thing as the cached approach I was talking about easier. That's easy. There's just a single field to manage. Object pools, there's a bit more to it. There's things like LRU caches that you can use to make this easier. But you know, figure out the right trade-off for your code. Arrays. Array list is pretty good. I tend to use it a lot. It's one of the nicer and more streamlined collections for storing stuff there. You keep adding to it. It'll reallocate when necessary. But if you just have a statically determined size collection that you need, array itself tends to be more optimal than array list, right? It doesn't need to allocate things in there. It's just got the array itself and then the objects that you put in it. So consider using arrays. They're just a bit more streamlined and optimal, and don't do as much churn for reallocation that collections would do automatically. Speaking of collections, I would encourage you to check out the Android collections. So the traditional Java programming language collections, they're all very powerful and useful, and they're probably still the right thing to use for large collections like hash map. Awesome if you have a really large amount of data that you need to store. But check out array map instead. If you actually just have a smaller collection, it avoids a lot of the boxing as well as the allocations that are inherent in hash map itself. So there's a bunch of collections in Android. There's array map in the support library. There's simple array map. Then there's sparse array. There's actually a bunch of sparse things: long, sparse, long, int, sparse, long, int. Lots of different combinations, but they basically use primitives as keys instead of the auto-boxed Java language versions of those, like not capital L long, but instead a primitive long. Wouldn't that be nice? Methods that mutate. This is another pattern that I think traditional Java programmers walked away from years ago, maybe holding their nose. In general, so let's say you want to pass in an XY and you want to get a point return because you need that point data structure to pass into some other method, right? So you have this utility function. I'm going to pass in XY. I'm going to get point back. Really stupid example. You could create your point on your own. But to illustrate the point, so traditionally, you would pass in XY, and it would allocate a point, and it would pass it back to you. Not a big deal. It's just a temporary object, right? Again, if you're in your inner loop, allocating is in general bad. Wouldn't it be nice if you didn't have to reallocate that thing all the time? That's just a temporary object. So instead, what you can do is keep a cached object in the caller, and then call a mutating version of that method instead. So instead of passing in XY, maybe you pass in XY and a point data structure, and then it fills in the data structure. And then that gives you the option to allocate it on the fly if you really want to, or to keep it and use and reuse a cached object instead. So if you look through the Android source code, especially in the framework, you'll see a lot of instances of this internally where we'll pass in a rect that gets filled in during layouts or whatever. And this is specifically to avoid the temporary allocations that are necessary to pass back richer data than simply a single primitive return value. And speaking of primitives, we have primitive types. We really like them in Android. In general, if you use primitive types, you're going to avoid all the boxing that's inherent in using the object equivalence. So if you write a method that takes a capital F float and you're running an animation or doing a calculation that has a primitive float, when you call that method, it's automatically going to box. It's going to create a capital F float out of it. There's slightly more overhead in getting the value of that. I'm not as concerned about that. I am concerned about creating garbage, creating these small temporary objects when you really didn't need to. So as much as you can, stick to the primitives. The collection classes obviously use the object types instead, so you can't really get around it there. But for all of your internal methods that aren't using collections, there's no reason to not use the primitives instead. They just tend to be a lot more streamlined and avoid the memory situations that we're talking about. There are a lot of language things that you can trip over without really realizing why. Iterators is one of my favorite examples. So I love the for each syntax. I don't know why it's called the for each syntax since there's no each in the language. Somehow we adopted that way of referring to it, and then you go looking for the primitive, and it's not there. They should just maybe call it a for. So it's very convenient. It came out in JDK 1.5. You say, for object O in this thing, and then it iterates through that collection. Very convenient. What's going on under the hood, though, this is syntactic sugar. It is creating an iterator for you, right? So it's allocating that object, and then it's doing the normal iteration using that iterator object. The iterator approach was kind of ugly and obtuse. I don't think people enjoyed using that. The for each works around that. It makes a nice streamlined thing, but it's still doing the same thing under the hood. In particular, if your collection is empty, it's going to create an iterator anyway. Right? It does not know that it's empty until it creates the iterator and then tries to get the first item and then says, oh, you're empty, you don't need to do this. So one of the optimizations that we did along the way to creating the new animation system in Honeycomb was to eliminate all the allocations that were going on in every frame. So we have this new animation system. We use this tool internally called Allocation Tracker. I would encourage everybody to use this to make sure that you're actually using memory correctly. So I would start the animation, I would start allocation tracking, I would collect the allocations, and then the animation would finish, right? I don't care if we're allocating at the beginning and the end. To some extent, that's unavoidable, right? This is Java. It's a memory garbage collecting language. You're going to allocate objects. What you don't want to do is allocate during the animation, like during the actual frames. And then I saw that on every single frame, we were allocating objects for listeners. What was going on was we have this view tree observer where you can listen to various events going on, layouts, pre-draw, draw, the things that are happening in the view hierarchy. And on every frame, we would say for view tree observer, listener, whatever, in this collection, then we would iterate through and we would do something. In general, nobody actually added a listener. It's not typical to have a listener there, but we would create an iterator on every single frame anyway because that's what for each did for us. So there's one specific case where it doesn't do that, which is if it's a primitive array, it actually does the right thing and will not create an iterator for you, so yay. But otherwise, it's kind of a good thing to maybe avoid if you're not really sure whether it's going to create things. And you can certainly go back to the old approach of doing an actual for loop instead and just get the items in the array, and then it doesn't advance to the first one if it didn't need it. Or if you use it, just be aware of when it's actually going to cause an allocation when you don't want it to. Wait, let's go back. Yeah, this one. So let's talk about enums. No more. I'm really tired of this topic at this conference. Go to the article and read. There's nuances to using them. Please understand the overhead inherent in enums and make the right decision for your code. Moving on. Finalizers. So one of the things that's not obvious about finalizers is nuances in the language spec mean that to finalize any object, we actually need to do a GC twice. So whenever you have a finalizer declared on your class, you're basically forcing a future GC twice. And you kind of want to avoid every single one, so why are you forcing two on the system? There are particular situations that really require finalizers. We do use them internally, specifically when we have native objects that need to be cleared. So we need to know when that thing went away so that on the native side, we can go ahead and free the native memory associated with it. So that's a valid use case for it, but I would say try to limit the number of valid use cases and definitely eliminate finalizers when you don't need them in other cases. They may be convenient, but there are better ways, certainly from the memory standpoint, to do what you want to do. Static leaks, this is one of my favorites. I may or may not have caused leaks in activities in some of my code. I should do a deep dive into the way that that hash map or weak hash map works. So there's a situation where I needed to store information about listeners associated with views, and I said, well, I know that weak hash map uses a weak reference, so when that view goes away, which is what I was using for my key, then I know that everything will be collected. Turns out that's not true. The way that weak hash map works, it actually had a hard reference to the key. It had a weak reference to the value, which kind of turns my head in knots. But the end result was that the activity would undergo a configuration change, so the phone would rotate, and it would tear down the activity, and it would come up with a new activity, and all that old stuff went away, except that I had a static weak hash map, which had a reference to the view, which implicitly has a reference to its activity. Bad thing in general. So beware of static leaks in general. The real problem here, besides my ineptitude and misunderstanding of how weak hash map worked at the time, was that the lifetime of the process is different than the lifetime of your activity. This is something I've hit again and again on Android. I tend to think of, when a window comes up, when that, that basically that application object that I'm working with, which is, the activity in my mind is sort of synonymous with application. That's the first problem. When that comes up, surely that is, that's where all my static objects live. They don't. They live in the process itself, and the process is long-lived. So when you undergo a configuration change, we rip down the activity, and we pop up another one, and it's in the same process. So if you have a static object there, whether it's a weak hash map or something else that's holding on to something it shouldn't in the old activity, it will continue to hold on to it. So static can be the right thing to use in some situations, but is really dangerous because just know that it's going to live a lot longer than the activity that you think you're storing things associated with. Static initialization is a good thing to avoid in general, especially for expensive allocations or expensive operations. The problem that we see is that when a class gets loaded and then does a bunch of static work, it's going to do all that stuff right now. This causes a problem, for instance, when you launch your activity. Right, so we're going to launch, we're going to try to launch as fast as possible, and then it loads this class, which does a whole lot of work that it really didn't need to. Why not do some of that stuff lazily? If you didn't actually need to, initialize the database, whatever, at that point, why don't you wait until a better time instead of forcing that to happen immediately? Okay, so third-party code. We've seen this one a lot where, again, something that traditional Java developers will do is bring over their libraries and their approaches from the old world. Oh, I really like this dependency injection library. So a common one that we've seen is Juice. Really powerful, very flexible, people love to use this, and then they'll start using that. It was not written for mobile, right? It does a whole lot of reflection, and I haven't really talked about reflection yet. Big secret, reflection sucks, okay? It has a lot of overhead associated with it, a lot of allocations, as well as just performance overhead. So in general, we tend to avoid it. Everybody kind of knows that, right? You don't really do reflection unless you need to. But a lot of these libraries that you're dragging in are doing it on your behalf. So the general tip here is to not use a library or third-party code in general unless you know that it was actually written for mobile. Because if it wasn't written for mobile, it's probably using a lot of the patterns that we're telling you not to in your code. So why are you using it indirectly in someone else's code? If for dependency injection, there have been a couple of libraries written since that are more tuned to Android. There was the Dagger library, and more recently there's the Dagger 2 library. I would suggest you check those out if you really want that functionality. And in general, just look for libraries that, I wish we had like a logo saying mobile friendly, but you can look for that logo. It doesn't exist, but look for the logo. Otherwise, just make sure that you actually know what that library is doing. The other problem that we've seen with third-party code is if you're using a really large library, chances are there's a dependency graph in there where you're dragging a lot of stuff that you don't necessarily need. Like if you are using, library foo because you really like that, collection class for managing this particular thing, and then all of a sudden it added, 20,000 methods to your method count and a whole lot of APK size just so that you could use that one collection, probably not what you want in your application. So just be as concerned about your library code as you are about your own code. So there are mechanisms that Android provides to help you with memory concerns. One of them is trimming memory. So the system will tell you when it's getting low on memory, and you should really respond to that, because it's not just telling you, like, oh, by the way, I'd really love some memory. It's not a casual conversation. It's saying, I need memory now. Could you please free some? Because otherwise, bad stuff is going to happen, right? So when it goes out, it reaches out to the activities running on the system, the processes, and says, we're running low on memory. Can you do something about this? And there's various levels of it. So you can sort of, set your warning and panic appropriately. But if you're keeping cached thumbnails around, just in case, the user wanted to do a fling, but right now you're running in the background, you don't need those anymore. Maybe it'd be a good time to jettison those, because if you can make yourself smaller, then maybe the system can get back the memory that it needs so that it doesn't have to go killing activities like yours. Right? So pay attention to the trim callbacks and do something about them. Isload device is a method on, I think, Activity Manager that tells you whether the system, at the moment, it means this has 512 memory in it. So if you really need more memory to have the best user experience, but you also want to work adequately on 512 meg devices, then you might call this method and set the way that your application behaves accordingly. Avoid large heaps. There is a way to ask the system for more memory, and sometimes this is necessary. You're a video playing application where the videos simply won't fit into the standard heap, or you're doing image manipulation with massive images, whatever it is. There are some corner case situations for which this was introduced, but it also tends to be a backdoor for lazy developers who are like, well, but I want more memory. It's easier. Yes, it is easier, and it makes a horrible experience, because the more you allocate for your process, the less everybody else gets, and then it goes back to the original point. So don't use it unless you actually really need it, please. Don't keep your services running. They can continue to run in the background, but if they exist just for a particular reason, then finish that purpose and then get out of them, right? Otherwise, they're just sitting there doing stuff. If nothing else, they're taking up memory in the background, meaning that there's less available for everybody else on the system. And then finally, optimize for code size. So this comes in a lot of ways, but it makes your APK download better, certainly, but it also decreases the amount of stuff that you're loading into memory for your system. So just be smart about how much memory you're taking up. So I want to go over some of the tips that we have in user interface. This is sort of a grab bag of things. Don't overdraw. There's a tool on the device called Profile Overdraw. I don't know what it is. Colt? Profile what? Profile GPU Overdraw. So you can see what the overdraw is on the device. It paints in a lovely palette of pastel colors. It will indicate to you how many times each of the pixels is being drawn on the screen. The problem is, so Android uses a common rendering technique called painter's fill algorithm. I guess because painters used a lot of rectangles or something, where basically we will paint all the stuff that you tell us to in the order of back to front, right? Because that's going to result in the correct display for the user. So you got a window background, great, we'll paint the window background. You have a container covering the window, great, we'll paint the container with its opaque background. Oh, you have another container covering that, that's great, we'll paint that one too. You have a list view, which has a background, we're gonna paint the background. Oh, all of your items have background, and all of a sudden, when you finally get to like the text in a list view, you've painted each of the pixels in those characters 5 or 6 times. That's something that the GPU doesn't really like to do, right? That was a lot of wasted effort in there. So what you really need to do is actually figure out what opaque objects are completely covering what other opaque objects, and maybe eliminate some of that overhead there. So you've got the window background, great, use it. Set it to the background color that you want, and then don't have an opaque background on the containers that are sitting on top of it. So take a look at your nested hierarchy there. See what the organization is of containers, as well as the opacity of the backgrounds that they're using, and then do the right thing there to make sure that we're drawing as few times as possible on every pixel. So use the tool, see what your overdraw is like. Red is bad. I'll give you a little tip. Red is bad, and then do something about it. Avoiding null window backgrounds. So one of the tricks to avoid overdraw ends up in some artifacts that you should be aware of. So people will eliminate the window background because they're like, great, then I don't have the overdraw of like painting the window and then also painting the first container on top of it. It'll just paint the container. That's true. On the other hand, sometimes then you have an artifact where all we have to paint is the window itself. So like we're animating in, the keyboard, the IME is animating in, and the window manager is going to handle painting the window. Or when we're launching the window itself, the activity is not running yet, we're going to be animating in the starting window, and it's empty. There's like null. The window manager has nothing to paint. You're going to end up with an artifact on the screen. Either it's going to draw black, or on some GPUs it may draw garbage on the screen because there's undefined contents in that buffer. So the window background is there for a reason. It's there to tell the window manager what to paint on the screen when it has no other information about the activity. So keep the window background, but to avoid the overdraw issues, see how you can use that window background to do the right thing instead of then having an opaque background on the container that overlays the window. Also, avoiding disabling the starting window. This is another situation that results in some artifacts where people will disable the starting window because they didn't want that blank window up before their activity launched. But again, the window manager doesn't know what to paint if we don't have a starting window. I would say instead actually use the starting window more effectively. You can brand your application with this. We've seen particularly ineffective approaches where someone wants a splash screen before they get into their activity. Maybe that gain took a couple of seconds to launch or whatever, so they're like, okay, well, we'll have a splash screen experience here. But then they get this weird experience where window manager doesn't know what to paint, so it doesn't do anything for a while because there's no starting window, and then a splash screen starts after a second or so with this completely different experience, and then the game starts with a completely different look. Pretty awful. Or in some situations, it gets even worse where like they kept the starting window because they didn't actually understand what it was. They have a starting window, and then they have a splash screen that's completely separate. And then they have the game screen. So then you have 3 completely different experiences over time, which is, nice if you want different experiences, but kind of sucks. What they should actually do instead is remove their splash screen and take their logo, take their branding situation, and use that as the background on the starting window instead. Then they get the benefit of having the starting window so that the system knows what to do before the activity is actually up and running. And then they also get to brand that as well and have the splash screen experience before their application starts. There's some tips about avoiding UI stalls. So the UI thread really likes to run and keep running. Otherwise, the user is going to sit there looking at a skip frame while it's actually busy doing something that it shouldn't be. So inflation tends to be expensive. So try not to inflate when you don't have to, or try to minimize the amount of inflation happening. If you have a really complex view hierarchy, maybe you didn't need all of that all the time. Maybe you could actually use view stubs in there and inflate other stuff on the fly as necessary, instead of having like, I don't know, Play Store like hierarchy that gets inflated on the fly whenever you launch your activity. That would be nice. No, handling events. When you get an event, it's nice to do less expensive operations. It's nice when someone clicks a button if you don't actually make a network call in general or go to the database. You kind of want to do that stuff asynchronously off the UI thread because those events are being processed in the same thread that's handling your animation events, your input events, as well as your rendering events and layout. Like all of that stuff has to happen on the UI thread. So anything that you're doing that's not visual, that's not UI related, should really happen elsewhere. Even if it will end up in data that does populate the UI, which a lot of this does, like, they click on the button, that means, some transaction where we need to repopulate the data that the user is looking at. That's great, but you don't have to do it synchronously, right? So you could spawn an asynchronous task, async task, or loader, or whatever, to go get that data, and then when it's back, then you can populate the UI. In the meantime, the user was actually able to interact with your application, and it didn't seem so janky. Measuring and layout is quite expensive. It's good to avoid it, particularly during animations. So if you wanted to, let's say, animate an object to move from one location to another, you could actually animate the layout params, right? You could change the layout params that were causing that thing to be positioned in the window. You could, and that's kind of the physically correct thing to do. Well, change the layout params. That forces a relayout, and then it'll figure out where it's supposed to be, and then it'll draw it at the correct place. And in the meantime, it's going to run a lot slower than you wanted it to. You're going to miss frames in there depending on the complexity of your hierarchy. It's a lot better to actually animate with post layout values like translation X, translation Y. Don't change the layout params, which force a layout. Instead, animate something that makes it visually correct, and then fix up the layout at the end. Or a typical technique that we use in animations is run layout, figure out where it's going to be at the end of the animation. So it'll run layout, it'll figure out where it needs to be, and then you've set an on pre-draw listener on it. And then in your on pre-draw listener, you say, okay, well, I know I want to animate to this other spot down there, so I'm going to run an animation, basically rewind to where it was before, and then run forward to the new layout location. So basically running translation Y from -100 to 0. This is essentially the approach that we use in the transitions package, right? We put it on pre-draw listener, we figure out where it was, we figure out where it's going, and then we set up the animation to rewind and then play forward. Drawing, in general, that's related to the allocation concerns and the amount of operations you're actually doing in the on-draw, and then the animation concerns in general. Just be aware that when you're in the middle of an animation, every expensive operation you're doing or every memory allocation could be contributing to missing a frame. It may not seem like that big a deal, like 30 frames a second, 60 frames a second, it's still moving on the screen. The real problem comes in when it's inconsistent. So if you're typically able to get 60 frames a second, but eventually a GC kicks in because you were allocating a bunch of stuff in on-draw or whatever, then there will be a skip frame in the middle. So yeah, 30 frames a second is reasonably smooth if it was consistent, but going from 60 down to 30 and then back to 60 causes a hiccup that's very noticeable to the user. In the middle, it's going to pause just slightly and then skip forward longer than it would have if it had a smooth frame rate instead. Avoid complex view hierarchies. I alluded to this before. Like, don't have more views than you need. Don't have deeper nested layouts than you need. I pull up some applications in Hierarchy Viewer. Who's used Hierarchy Viewer? Okay, good. Getting there. We're getting there. We'd like 100% someday. It's a really good way to sort of get a mental model of what your application looks like on the inside, what the model and the containment hierarchy is like. I've seen some applications that have this, long tail of containers where they've got a relative layout, and then there's a linear layout on the side of that, and then there's a frame layout, and like each one of these things, like it had a purpose. Somebody had a reason for that. Like I want to, have this background here, and then there's this other layout that's tuned to, have the right fringe effect on. I don't know what their reasoning was. I'm sure there was a good one, but not good enough. Right? What you want to do is figure out how to have, the single container that you needed instead of the long nested thing that's simply going to cause more overhead for inflation, for layout traversal, for rendering, all of this stuff. Every layer is, in the hierarchy, is just causing more work for the framework every time we need to redraw you. Also, relative layout is probably the most flexible layout. It allows you to do the association with, sibling views and the stuff on the side, and I want to align this next to that. So it's the most flexible, which is why, unfortunately, it is the layout that we use when you create a new project in Android Studio. This is not something I'm real happy about right now. We would like to change this eventually. The problem is that relative layout causes us to measure twice, right? So if you are associating views with other views, that means we're going to ask all the views how big they want to be and where they want to be. Well, we're going to ask how big they want to be because we need to figure out where to put them. So we're going to ask all of them, and we're going to take all this information, and we'll crunch on it a little bit, and we'll say, okay, we know how big everyone wants to be. Now we have more information about all the relative locations and sizes of things. We're going to ask you one more time. So it's going to measure twice before it actually lays out. So if you have a relative layout at the top, basically you're measuring every view in the hierarchy twice. Or even worse, what we've seen is nested relative layouts. And then you basically double it for every layer in the hierarchy. So a relative layout sitting beneath another relative layout, you're measuring all the children of that nested one 4 times. Probably a bad idea. So if you don't need a relative layout, we understand that in some situations you need it. Usually not at the top level of your hierarchy. It's usually needed at a container level where you actually need the association of the siblings or whatever. So go ahead and use it when you need it, but be aware of the overhead of it. And try not to put it at a really high level, and certainly try not to nest it. Yes? Is it better to have a relative layout with a lot of views or a nested linear layout? It probably depends on, so the answer is always it depends. It depends on how high up in the hierarchy it is. So if it's sitting at the top, then it's going to cause all of that overhead to everything sitting underneath it. If it's at the bottom of your hierarchy, it's not going to cause that much, right? You're going to be measuring all the views, but you wanted to do that anyway, like you wanted those sibling associations. That's probably fine. Nested linear layout also has its own overhead associated with it, so it doesn't measure twice, but you just added a bunch of layers in there. It's also worth considering custom layouts at some point too. If you find yourself tying yourself in knots and adding more and more nested linear layouts to get the particular effect you wanted, you know, with all the right padding and associations between all the different sub-views and sub-containment hierarchies, at some point it's much more optimal to simply create a custom layout. So you subclass view group, or you subclass some layout that does most of what you want, and then you do your own measure and layout, and that'll probably save you time in the long run. Launch fast. Go ahead and try to get the UI up as quickly as possible. This pertains to some of the stuff I was talking about before, like not doing too much in static initializers, like not inflating all of the views that you might possibly need in the future. Instead, just get up and face the user with something quickly. Otherwise, you know, they've clicked the button, they've seen the starting window, and then 4 seconds later, they see your application. Horrible experience, right? Wouldn't it be better to be faced with a simple UI that could then populate itself later as necessary? Defer the extra work. If you didn't need those fields initialized, maybe you could actually initialize them lazily instead. And also measure cold starts. So when your application starts, it's important to understand the different dynamics of what state it was starting from. So when it is started from the first time after a reboot, that's what we refer to as a cold start. This means it's all the work that we had to do to actually read in the APK, to load all the classes, to initialize all the stuff, and then to do the first layout and rendering of that thing. There's the window animation, but you know, let the window manager deal with that. It's all the stuff that we're doing inside of your application to simply get to the first frame that is displayed. So it's important to understand how much time that takes and to measure it appropriately. So if you launch your application and then you hit the home button and then you launch it again, your application, depending on the amount of memory available on the system, was probably still resident in memory. So all we really needed to do was display it again. We re-rendered it, period, right? We didn't reload it. We didn't, you know, in a lot of cases, we didn't need to do another layout. We're basically just, you know, showing the same thing that we had before. So you're like, this is great. I can start in 50 milliseconds. I'm super fast. And then the next time you reboot, it takes 4 seconds. So what you want to do to really get a better measurement is actually kill the task, right? So go into recents and swipe it out of the way, and that'll get you most of the way toward the situation of a cold start from reboot. So get it out of memory. Make sure that we're actually dragging in all of the stuff again to really understand how much time your application is taking to launch. I want to talk about some of the tools that are important to use. Hopefully everybody uses most of these. Systrace, talked about a little bit yesterday. Colt talked about it as well. Super powerful tool, super confusing. There's so much information in there. There's so many options. You look at it and you're like, I see a lot of green. I see a lot of red. I don't know what to do about it. We added the tips, the little circular bubbles in the middle. I would encourage you to get the latest Systrace and play with that. Click on the tips and see what it's trying to tell you. In general, the problems that we've seen that we can do some amount of analysis on in the tool now for you tend to be common issues, like you're in the middle of an animation and you ran layout, or you're not reusing the view when getView is called on your list view. So some simple things that we noticed over and over and over again that we now fed into the tool so you can get for free. And then once you start using Systrace more, you start to understand, okay, well, these are the vsync pulses. This is, you know, the amount of CPU usage that was going on at the time. My thread is sleeping because, you know, it's tied to this other event in Surface Flinger, which was processing the GL. Like, there's a lot of associations that you can get over time and practice with using the tool. But it's really the only tool that we have that gives you sort of the big picture of what was actually going on in the device that was causing the jank that you see. And you can see the jank in the output there. You can see, you know, I've got regular pulses. I'm doing my perform traversals, which is the rendering loop in the UI thread, on every single frame, and then I skip 3 frames. Why? That's what you need to figure out so that you can fix the jank in your application. Allocation tracker, super useful for all of the memory stuff that I was talking about before. So obviously, we're using a VM here. Runtime that's going to be allocating objects. You can't avoid allocations. What you should try to do is avoid allocating during times when you know it could cause jank for the user. So run that animation and then see what's being allocated during the animation and make sure that all of the objects are not actually coming from your code. Ideally, there would be no allocations during the animation, but if you can't fix that, you can at least fix the ones that are coming from your code that don't actually need to happen during the animation. Trace view, there's two versions of it. There's a sampling as well as non-sampling. Instrumented? What was the other way they refer to it? What do you? The sampling means, okay, it's going to look occasionally and see where it's at. This has very low overhead, which means you're going to get reasonable times back for how long these various things are taking. But it's not going to give you the full call stack for where the code was at any point in time. So you want to use the instrumented version instead if you're trying to understand the code flow in how you actually got to this at that particular time. However, that has a fair amount of overhead associated with it just in each of the method calls. So make sure that you're not optimizing the wrong thing. Don't look at the raw absolute times that you're getting out of trace view if you're using the instrumented version, because the times that it's reporting for method calls is really out of whack with reality. I have optimized stuff before and saved 0 time in the end result just because it wasn't really giving me the right information. So it's useful for understanding the flow and for kind of relative times, but don't take the numbers too seriously if you're using the instrumented version. Hierarchy viewer, we talked about that. MAT, I would also call out the new memory analysis tool in Android Studio. Memory monitor, I think, there's a couple of new memory tools. One is memory monitor that just shows you the use of memory over time. The other one actually analyzes leaks and dependencies in the graph. So check that one out. It should be a lot easier to use and more tuned for Android dynamics than MAT, which is an Eclipse tool. So basically, to use MAT, you take a heap dump, and then you go into MAT and you basically see what objects are still alive that you didn't expect. So this is where you find out things like activity leaks. But as I said, there's possibly an easier tool to use in Android Studio for that. There's also an external tool put out by the folks at Square called Leak Canary that I would suggest you check out as well. Memory monitor, I just mentioned that for Android Studio. And then there's on-device tools. So those were tools that you run on the host, on your desktop machine, but then there's device tools where you can see in real time some of the information that you need to tune performance. There's strict mode, you can enable that and it'll do a red flash whenever your code is doing something that it shouldn't on the UI thread, like making a network access or disk access or whatever. GPU profiling, there's the overdraw stuff that we talked about. There's also the raw performance. It'll put colored bars on the screen to show you how much time you're taking in each of the various phases of rendering. So it'll show you, whether there's a spike at a particular time because you're getting, inconsistent results from this thing, or whether you're just consistently taking too much time, creating all the rendering objects or whatever it is. Duration scale, this is useful if you want to just slow down your animation so you can see what's actually going on the screen. I actually find screen record to be a much more useful tool for debugging animations because I really wanted to see it run in real time. It's just that my eyes don't work that fast. So I'll do a screen record and then upload the MP4 from the device, and then I can frame step it in some animation tool or just a movie player. And then I can see what happened on every single frame to try to track the artifacts or the problems there. And hardware layer updates, this is another visual tool on the device that shows you when you're updating information that is currently cached in a layer, which is generally a no-no. I would say that there's time for Q&A, except for the fact that the timer is running out right now. So thanks for coming.